Hi, welcome to another tutorial for Webots-Line. In the previous tutorial, we showed you how to install everything that you need in order to run the Webots-Line competition, which is the challenge you see in front of you run inside the Webots environment. We also introduced you to some of the sensors that you'll be working with when trying to tackle this competition. In this tutorial, we're going to work through some sample code to help you get your foot in the door when it comes to tackling this competition. So if you visit the GitHub repository for Webots-Line, the link to the GitHub will be in the description. And you come to the controllers folder, you will find three controller folders, example line tracing controller, example line tracing controller PID, and full sample. And each one of these folders contains sample code for you to work through to get a better handle on how to program inside of Webots. And each one does a specific task. This one does line tracing, this one does line tracing with PID, and this just works through all the devices that you might need to actually complete the rescue line challenge inside of Webots. In this video, we're going to go through the full sample code for you. And in case you don't remember, a robot controller is just some code that the robot will run in order to navigate and interact with the world inside of Webots. So if you don't know already, to download this entire GitHub repository, you're just going to go to this green download code button, the drop down, and you can press download zip. Once you click on this, a zipped folder will be downloaded, and then you just open it and extract it. And when you extract it, it should look something like this. You have a bunch of folders that reflect what you see in the GitHub repository. And again, to open up full sample, you just visit controllers, you visit the full sample folder, and then you can edit this .cpp file with whatever text editor you want. Webots provides its own text editor for you to work with, but I have it pulled up in Visual Studio Code just for a little better visual. So remember, if you want to run full sample.cpp, all you have to do is open up Webots and attach the full sample controller to your robot, and then hit play, and then it will run full sample.cpp. Later on in the video, we're going to give you a full demo on how to actually run the robot. But first, we're going to do a walkthrough through this entire code and see how to actually interact with all the different components within Webots Rescue Line. So we're going to start off with all the include files, right? When you're working with Webots, you have to have an include file for every single device that you use. And by device, I mean every motor that you use, every type of sensor that you use. So you can see here we have one for the robot, we have one for the camera sensor, we have another one for the distance sensor, and we have another one for motors, right? And if you want to use a different sensor like an accelerometer or a GPS, then you have to add another include statement for each one of those sensors, right? And the name of the header file is just the name of the sensor within Webots, right? Just with a capital letter, and you'll find the name when you open up Webots. From here, we have a pound include of IO stream. This is just for cout. If you prefer to use printf, then by all means go ahead, use stdio. And then we do a pound define a threshold for 100. We'll get to this later. So now we get into the main bulk of our code, right? The first thing we do is we have to create a robot object, right? And what this does is we use this robot object to call robot-related functions. So for example, if we want to get how much time has elapsed in the program, we would use the robot object to do so. So all we're doing is you can think of this as a variable if you haven't worked with objects or classes yet. So you can think of this robot as just a robot variable, and we're going to use those variables to call different functions. Right? And from here, we do the same thing for our left motor and right motor. Right? We grab the left wheel off of the robot, and then we store it inside this variable. And then we do the same thing for the right wheel. Right? And again, we're going to use left motor and right motor, these two objects, to call motor-related functions. And lastly, we're going to get the time step within our world. What the time step is as the simulation plays within Webots, it can't provide an infinite amount of frames per second, and it can only give you a certain amount of frames and a certain amount of updates per second. And what the time step does is it specifies how many milliseconds go by between every world update and every frame update, right? So if you have time step set equal to 100, that means 100 milliseconds are going to go by between every single update for the world, right? And right now we're getting the default time step. The default time step is always just 32 milliseconds, which is a perfectly fine number. Next, we define some functions to make programming a little easier for us. The first function that we define is the delay function, which just stalls out our program for a specified number of milliseconds. Webots does not come with an inbuilt delay function, but since we are able to get the elapsed time within our program, we can use that to stall out our program for some time. And how it basically works is it accepts a parameter, which is the number of milliseconds that you want to wait for. Remember, just 1,000 milliseconds in 1 second. And the first line just grabs the time at which this function was initially called, right? So in this init time, it stores the number of seconds that have elapsed when this function was first called. Next, it keeps pushing the world forward using this step function, right? If you ever see this robot time step, it's just pushing the world forward and just making sure that the world updates itself, right? And it keeps updating the world, and it waits until your current time minus your initial time, which is the time that has elapsed in milliseconds, is greater than the number that we passed in, right? And the reason why we've multiplied by 1,000 is because the robot get time function returns in seconds. So we want to convert that into milliseconds so it lines up with our parameter, right? So basically, when the time elapsed is greater than the milliseconds that we specified, then we're going to break out of this function, and we know we have paused for our specified number of milliseconds, right? However, you don't see any code within this while loop, right, other than pushing the world forward, other than updating the world. And what that means is if you have motors going or if you have sensors probing, they're not going to stop, right? If you have your motor set to spin the robot and you call this delay function, the motors are not going to stop, right? Because this delay function does not have anything to do with stopping motor speeds, right? So just keep that in mind. The next function that we define is a set speed function. It's very simple. It takes two parameters. The first one is the speed of the left motor that you want to set, and the second parameter is the speed of the right motor that you want to set, right? And then it uses the left motor and right motor objects, calls set velocity, and then sets the velocity to the parameters that we passed it, right? Each motor that you work with within Webots has its own maximum and minimum speed. And we'll get to that later, but just keep that in mind. If you start pushing the boundaries, you will get errors within Webots. So yeah. So now we're going to get into our main function, right? So just like we did with the robot object and the motor objects, we're going to create an object for every sensor that we need, right? And we're just going to go through the crucial ones. You can add more sensors if you want, and there actually are already some more sensors on one of the in one of the worlds, but we're just going to grab only the sensors that we need for this demonstration. Right? So that includes 3 of our color sensors. And you might note that, hey, this looks like a camera object, right? And that would be true. And the reason for that is when we were creating the robot, we wanted to add on a color sensor to obviously detect green during line tracing. However, Webots does not have an inbuilt color sensor that can detect, red, green, blue, and gray. So what we did was we took a camera and we made a really low resolution. And basically what that does is it acts as a sort of color sensor, because within the camera you can get the total red, green, blue value that your camera sees. So fundamentally, this really low resolution camera acts as a color sensor. And you can get the red, green, and blue values and even gray values from the image that your color sensor is looking at. So we have a left color sensor, right color sensor, and a front color sensor, right? So it forms a triangle. And its names are left color, right color, and front color, right? The names you can see within the scene tree inside of Webots. We'll show you that later when we actually run the full code. Next, we create a distance sensor object just for a distance sensor that's facing forward. It's called front dist, right? And note that for every single sensor we create, we use robot and then we get a specific type of sensor. So here it's get distance sensor, over here is get camera. Right? And now we're going to get the last motor. This motor controls the scoop. The scoop is the device that you pick up balls with, right? You'll see what I mean when we run the program. And lastly, we get the camera height and camera width of the color sensors. So if you really think about how a camera normally works is it returns an image, right? And the image is made up of a bunch of pixels in rows and columns, right? And basically all camera height and camera width is camera height tells you how many pixels tall the image is, and the camera width tells us how many pixels wide the image is, right? But since we changed our color sensors to be 1 pixel cameras, it's only 1 pixel high and 1 pixel tall, right? So this will return 1 for camera height and 1 for camera width. So now we move on to enabling our sensors. And the only reason why you need to enable your sensors is just to tell it how often to update. Right? So if you remember from before, we specified our time step was going to be the default time step, 32 milliseconds. And what that basically means is we want our world to update every 32 milliseconds. So we just do the same thing with the sensors. We tell our sensors, we feed a time step, meaning update the value of the sensors every 32 milliseconds, right? So you see here we have our 3 color sensors and then our distance sensor. Next, we set our 3 motors, we set their positions to infinity. And the reason why we do that is Webots provide something for motors called position control. And what that basically means is you can tell a motor, if you have spun this amount of radians, then I just want you to stop on your own, right? Without any code, it's just going to stop on its own, right? So if I say like set position to 2 pi radians, right? 2 pi radians is just 360 degrees. So what that basically does is after the motor rotates 1 full time, it'll just lock itself, right? And it'll freeze right there. But since we don't want to do that, we want to allow our motors to rotate infinitely. We just set the positions to infinity in caps, right? And to kick things off, just to make sure nothing goes crazy at first, we're going to set our speed. We're going to use our set speed function and make sure that our left motor and right motor and our scooper motor all have a velocity of 0. And this set velocity function takes values in radians per second, right? So right now I'm telling it to spin at exactly 0 radians per second. And you can also see here that the motors for the particular robot that we provide for you is 12.2 radians per second, right? So if you want to go at 100% forward, then you just have to set your velocities to 12.2 radians per second, right? And if you want to go full speed backwards, then you just set it to negative 12.2 radians per second. Right? And then here we define quite a few variables that we will talk about later as we work through our code. So now we move on to our main while loop, right? So within Webots, for every robot controller, they will always have at least one while loop that looks something like this, with the step function being called. And all this is just saying is, within this while loop, I'm going to continuously update my world by calling this step function. And all this condition is while my simulation is running, right? So if I stop the simulation, then it's going to break out of this while loop. Right? So while my simulation is still running, I want to do all this. And we start off by getting all the color values that we're interested in from our color sensors. So the first thing we do is we get the gray value of our front sensor, our left sensor, and our right sensor. And we store them in front gray, left gray, and right gray. And the gray value of a sensor is very simple, right? It's just a value from 0 to 255 based on how bright the floor is, based on how bright the image is that the color sensor sees. So if our color sensor is pointed at straight white, it should return close to 255, right? And if it's looking at straight black, then it should return about the value 0, right? So those are our 3 gray values. Then we get the greenness of our left sensor, we get the redness of our left sensor, And we do the same for our right sensor. We have the greenness of our right sensor, and then we have the redness of our red sensor, right? And we're going to use this later for detecting green while line tracing, right? And the reason why we get red, we'll explain in a second. But anyways, the image get green function and the image get red function all work similarly to image get gray function, except for image get green, it'll return a value from 0 to 255 based on how green the image is that the color sensor sees, right? So if the color sensor sees a lot of green within its field of view, then it'll return close to 255 for image get green. And if the color sensor sees a lot of red in front of it, then it'll return a number close to 255 for image get red. And we store it in our left green, left red variable. So in summary, we have 7 variables. The first 3 variables store how light or dark the floor is that the color sensor sees. And the left green and left red variable stores the greenness and the redness of the floor that the color sensor is pointing at, right? That the left color sensor is pointing at, right? And the left green and the right green and right red variable store how green or red the floor is that the right color sensor is looking at, right? And each one of these values all go from 0 to 255 based on either dark to light or non-green to green or non-red to red. So now we actually get into identifying what it is we're actually looking at, right? So right here, we're going to check whether each sensor sees white or black. So we first check the front gray sensor, right? And remember how I told you that the front gray variable stores a number from 0 to 255 based on how light the floor is that it's looking at, right? And we also defined a threshold up here, a threshold macro, to be 100. So basically, all this is saying is if the front gray value is higher than 100, right? If it's closer to 255, then we're going to say that the front sensor sees white, right? Otherwise, that means that the front gray sensor sees a value lower than 100, which is closer to 0. We're going to say that front light sees black. And we repeat the same thing for all 3 other sensors, right? If my left sensor sees a gray value above our threshold, above 100, then we deem that our left sensor is looking at white. Otherwise, it's looking at black. And then we do the same thing for the right sensor. Right? If it's greater than this threshold, then it's white. Otherwise, we're looking at black. Next, we're going to try and figure out whether our left sensor or right sensor sees green. And the way we do that is we take the green value that we had before and we divide it by the red value. And the reason we do this is, if you think about it, if our color sensor is looking at a patch of green, right, that means there is going to be a lot of green and not that much red. So if we have a lot of green and not that much red, if we take our green value and divide it by our red value, we should get some decently high number. The number should at least be above 1, right? Because if our left green value divided by our red green value comes out to exactly 1, that means our color sensor sees equal parts green and equal parts red. So by saying left green divided by red, we're basically saying, is there more green than red in our picture by amount of 1.3, right? And if it is above that amount, then we say, okay, our left light is actually seeing green. Then we do the same thing for our right sensor, right? If our right color sensor sees more parts green than more parts red, then we're going to say it is also seeing green. Okay, next we're going to check for evacuation zone, right? And if you come to this picture, you'll see that the entrance to the evacuation zone is marked by a gray stripe, right? And the exit to the evacuation zone is marked by a green stripe, right? So basically all we're going to try and do is check for a gray stripe and then check for a green stripe. So to check for a gray stripe, we're going to basically say if our left sensor and our right sensor sees a sort of grayish. And the thing about gray is it's somewhere in the middle between black and white, right? So remember, black is 0 and white is 255. So we're looking for a grayish value, which is somewhere in between 0 and 255. And what we're going to determine is that if our left sensor sees a value between 150, 155, and 175, we can reasonably assume that that's gray. So all this is saying is if our left color sensor sees a gray value greater than 155 and less than 175, then our left sensor sees gray. Then, if our right sensor does the same thing, if our right sensor sees greater than 155, and our right sensor also sees a gray value less than 175, then our right sensor also sees green. Or our right sensor also sees gray. Then, this entire if statement is just basically saying, if my left sensor sees gray and my right sensor sees gray, then I'm going to say I have entered the evacuation zone, right? Followed by a print statement. And we're going to do the same thing for checking for an exit, right? So basically, this if statement is saying is if I am currently in the evacuation zone, right? Because you can't leave the evacuation zone if you're not already in it. So if I'm in the evacuation zone and my left sensor sees green, remember this is just the same criteria we used before to determine singular green. So if my left sensor sees green and my right sensor sees green, then I'm seeing this strip of green right here, right? Because both sensors, when you exit the evacuation zone, assuming you're lined up properly, both sensors would see green. So if that's the case, we can reasonably assume that we've seen a green strip, and we can say that we're no longer in the evacuation zone, and we give a little print statement, right? And if you're concerned about this activating, right, because you definitely know that there are instances where both color sensors can be on green while line tracing, right? That's one of the intersections where you have green on the left and a green on the right. But you don't have to be worried about that activating here because we have one more requirement. We have to be our requirement is we have to already be in the evacuation zone, right? And if we're still line tracing, then we know for sure that we're not in the evacuation zone, right? So this if statement will not go through if you see double green while line tracing, simply because of this check that we're inside the evacuation zone. So now what we're going to do is we're going to check for an obstacle, right? And right off the bat, we know that an obstacle only occurs when we're line tracing, right? So if our front sensor sees something, it could either be a obstacle or it could be a victim, one of the balls inside the evacuation zone. But we know that if we're not in the evacuation zone, that means we're line tracing. And if we're line tracing and we do see something, we know that that's an obstacle. So all this if statement does right here is it's saying is if we're not inside the evacuation zone and our front sensor sees something, right, our front sensor get value is less than 20, then we're going to say obstacle equals true, aka there is an obstacle, right? Otherwise, we're going to say obstacle equals false, which just means that there is no obstacle in front of us. Right? Then we're going to check for victims. So this is basically the same condition, except we have to be inside the evacuation zone. So this just says if we are inside the evacuation zone and our front sensor sees something less than within 20, then we're going to raise and lower our scoop, and we're going to do that by taking our scoop variable and we're going to set it at a velocity, set it to rotate at a velocity of +1 radians per second, right? So it's just going to go up, 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 up for 1 second, right? We take advantage of our delay function that we wrote earlier. Right? And once it's reached its peak, what we're going to do is we're just going to lower it back down, just because we're just trying to work with it. We're not trying to actually get anywhere as of right now. So we're going to take the scoop and we're going to set it to rotate at a velocity of -1 radians per second. So it is just going to rotate, come back down, 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 for 1 second. Right? And once it reaches its original position, then we're going to make it stop rotating so it doesn't, rotate into the ground. And at the end, we have one big print statement where we basically print some values that we're interested in, right? So we're gonna say like, oh, what's the grayness of our left color sensor? What's the grayness of our front color sensor? And what's the grayness of our right color sensor? Right? And we're also gonna print out whether or not we see an obstacle. And whatever values you're interested in, you can change this up by all means, right? You can add variables to this list, and then just set them to different values throughout this code, and then just print out whatever you're interested in looking at, right? So let's say you're interested in seeing if we saw a victim, right? You could create a new variable, set it equal to true within this if statement, and then print that variable out inside this big print statement. So you guys could probably tell that within this program, we didn't actually do any of the challenge. We didn't try and navigate around any of the obstacles. We didn't try and line trace anything. We didn't try and deliver the balls. And that was the point of the sample program. All the sample program does is it familiarizes you with how to work with stuff in Webots, right? We touch through all the sensors, the motors, all that sort of stuff. So here should be a good starting spot for you to work with, right? So you can sort of understand how to detect the various, obstacles within the world, and then from there, how you negotiate with them is up to you. All you have to do is start calling your set speed function to move your robot around, and from there, the challenge should be relatively feasible. So if you go back to your folder that you extracted earlier, and instead of going to controllers, now you go into worlds, you'll see a bunch of WBT files, and each one of these are worlds that you can run. And I just opened up AutoLac 5 right here in front of me. And this is one of the sample worlds that we provide to you for testing. Right, so you can see that you have line tracing, you have obstacles, speed bumps, seesaws right here with checkpoints, these yellow things. You have an evacuation zone with live victims and dead victims. You have your delivery corner. You have intersections. And then you have your red marker as the end, right? And basically what we're going to do is we're going to run our sample code, right? So just to go through a few things before we actually run the code, this left window over here is called the scene tree, right? And basically the scene tree is just a list of all the objects within your world, right? And it gives you a lot of details about those objects. And we're going to look into in depth at our robot that we have right here. And it's just called the player 0 robot. And with the drop down menu, you'll see a whole bunch of attributes associated with it, right? You have its translation, which is its position, its rotation, like what direction it's facing, its scale, which has to do with size, children, which has all of its attachments. If you actually hit the drop down menu on children, and you hit the drop down on extension slot, and then drop down on children after that, you'll see a list of all its attachments, right? So you can see that we have a scoop attached to it, we have 3 distance sensors attached to it, we also have 3 color sensors attached to it, right? So if you ever want to add more sensors to your robot, you just come to this children under extension slot, and you hit the plus sign up here. So our window appears, and if you go under base nodes, you'll see a whole bunch of sensors that you can work with. And these are all Webots provided sensors. Right? You have a touch sensor, you have a compass, you have distance sensors, emitters, all sorts of good stuff. And if you actually go under proto nodes, we provide to you a color sensor and a distance sensor. Right? Remember we talked earlier about how pure color sensors that give you, R, G, and B don't exactly exist in Webots, right? So we made a color sensor. It's called a proto color sensor proto for you, which is a 1 pixel camera. Right? I also made a distance sensor because if you add a sensor that is provided by default inside of Webots, so if you use one of these, they don't come with physical objects, right? If you add a sensor, it's going to look like nothing. There's going to be nothing there. There will be a sensor that you can work with, but you won't be able to see anything. However, if you use either one of the protos that we provided for you, whether it's the color sensor or the distance sensor, you will be able to see some shape, right? So for the color sensor, it's going to be a cylinder, and the distance sensor is actually going to look like a distance sensor. So yeah, those are the sensors. So if I pull this back up, you can run through the other attributes, right? You have your name of the robot, you have a description you can add, you have its physics, and the one we're actually most interested in is the controller. This controller bullet point right here basically determines what program your robot is going to be running, right? So in our case, we want to be running full sample .cpp. So all I'm going to do is I'm going to click on the controller. I'm going to click on select. And I'm going to find the name of my robot controller that I want to run. Right? And in our case, it'd be full sample. Right? So I click on full sample, I click on OK. And then you can see it changes to full sample. Right? So now our robot is set to be running our full sample code. Right? I'm just going to come out here and I'm going to save my world. And because this is C++, you need to build your program. And the way you do that is you can open up Webots text editor. So if I go to tools and I can click on text editor. From here, if I use the open file button, I can open up my CPP file within the Webots text editor. If I go to controllers, and then I go to full sample, I can open up the CPP file right here. Right. Then, if you go to this gear at the top and click this gear, that will build the project for you. Right. So if I hit the gear, you can see that a make goes off. Right. It's updating full sample, and it's just rebuilding everything. Right. And the make file, if you're familiar with make, is provided for you when you use the wizard to create a new robot controller, right? So if you don't already know, to create a new program, all you have to do is go to wizards, new robot controller, next, select what language you want to work in. Webots GCC makefile is fine, and you give it a name, right? You go to next, and then that already exists. I'm just going to call it my controller 1. Go to next, and you can hit finish. Right, and I recommend you use this way, use the wizard that is, because it provides to you all the necessary files, right? So for those of you who are familiar with C++, it takes more than just a CPP file, right? You also need a make file for our case, right? So if you go through this wizard and the new robot controller, it provides for you the entire project folder and the make file already in there. So all you have to do is hit the gear, and everything should build properly. Right? So you can see that we got a compiler error. We're just missing a semicolon. So if I go back to Visual Studio, Visual VS Code, and I come down to, let's see, where's the line? 80. You can see that I was missing a semicolon. So as you can see, the build works all good, right? And it'll give you any compiler errors inside your console down here. Right? So if I go for another rebuild, don't mind that it's empty. It's just that when you're working on a separate text editor on the same file, that sometimes it'll go blank, right? So these are just warnings, no errors. And I can reset my program, right? From here, I'm just going to click play. And my robot controller should start running. If you ever get this error, the process crashed sometime after starting, you can try resetting again. And you can see that now it works. Right? So I pause it real quick. You can see that it's printing out. My left sensor has a gray value of 207, which is pretty reasonable, right? So if I zoom in here, my left color sensor right here is above white. Right, so it's pretty reasonable that my left gray value is pretty close to 255. Right, it's 207. Right, same thing with my right sensor. Right sensor is seeing 207 because it's also on white, and then my front sensor is on black. Right, and then there's no obstacle in front of it clearly, so obstacle is still 0. There's O. And remember, these print statements are coming from this big C out. And you can change it however you want to see whatever values you want to see. So I come back here. Yeah, one thing I do also want to mention is we're in the process of revamping this system so that you can have automatic scoring when you run, right? So if I hit play and your robot continues forward, we're providing automatic scoring system, automatic lack of progress system, so it'll reset by itself. However, during testing, there are absolutely times where you want to shut that off, right? You don't want lack of progress to go off automatically, right? You want to be able to control everything the simulation is doing. If that's the case, as it is right now, if you go back to the scene tree and you find the game supervisor robot, this guy right here, you hit the drop down on the bullet point and you find its controller bullet point. All right, so if I go into the game supervisor and I go to controller, you can see that it's set to game supervisor. This is the code that makes it do automatic scoring and automatic lack of progresses. To shut that off, all you have to do is hit select and then you click on none. And basically what that means is you don't want your game supervisor to run anything, right? So no lack of progresses are going to go off automatically, no scoring is going to go off automatically. So you're free to do whatever you want. So if I go ahead and hit play on my simulation, you can see that my program starts to run. Right? It's printing out the color values that it sees, and also whether or not it sees an obstacle. So for my left color sensor, you can see by the L, my left color sensor is above white. So it's pretty reasonable that it sees a high value, right? This 207 is pretty close to 255. Remember, 255 is just white. The same thing goes for my right color sensor. My right color sensor is also above white. So you can see that it also reads 207, which is pretty close to 255. And my front sensor is above black. So it prints out a B for black. And if you can, as you can see, as I move it around, as I move my robot around, by shift and clicking, you can see that the values continuously change, right? You can verify that they're all right by running it yourself. And just remember, the values that get printed out here are just a part of this big cout, this big print statement that we wrote earlier. Right? Also, if I want to test the obstacle, I can drag this to drag this close to something. I'm gonna try dragging this close to this wall right here. So we hit play. You can see that it now reads 1 for obstacle. So it does see something in front of it, which it can conclude is an obstacle. Obviously, it's off the line right now, so it's mistaking the wall for an obstacle. But in reasonable scenarios, if you were to drag it up against this obstacle, you would see that that it reads 1 for obstacle. One thing to note is that if you are searching for obstacle, it's probably a pretty good idea to get the scoop out of the way by setting it to some velocity and having it rotate out the way. Right. Talking about the scoop, we're going to try and get into the evacuation zone. So if I shift and drag it over here, I can hit play. If I slowly drag it forward, oops, not rotate it, if I turn it back, if I slowly drag it forward, at some point you will see that the console starts to print entered evacuation zone. And that's because the code we wrote earlier told the robot that if my left sensor and right sensor both see gray, this gray strip, then I'm inside the evacuation zone and it should print out entered evacuation zone. Remember, that is this code right here. Right. So if I continue to play, I can drag this, and as that, since we're in the evacuation zone, we are looking for victims instead of obstacles. So if it does see a victim, it should raise its scoop. Right. So if I get this real nice and close to a victim, it activates and raises and lowers the scoop. Specifically, it raises up for 1 second and raises down for another second. Right? So you can see that it detected the victim pretty nicely. So you can see that this full sample.cpp program deals with basically all the elements you'll find within Webots-Line. Right? For line tracing, we probe the 3 color sensors, right, which could give not only gray, black, and white, but also green, red, and blue if you really want. And it also dealt with obstacles. Remember, we had that distance sensor code. It dealt with evacuation zone by checking for the gray stripe to enter, use the distance sensor to check for victims, and then checks for the green stripe to exit, right? So it at least does detection for all the elements you'll see within Webots Rescue Line. However, it does not deal with any of the elements, right? It doesn't line trace, it doesn't get around the obstacle, it doesn't deliver the balls. It only interacts with all the elements you'll be dealing with within Webots-Line. Right? So all that means is full sample.cpp is a good starting point for you if you're not really clear on where to start. From there, how you deal with each element is up to you, right? You can set your motors to do to deal with obstacles or line tracing however you want, and all that is really up to you and your creative mind. Right. So I hope that was a good tutorial and a good start on getting into Webots Rescue Line. I hope you find this challenge enjoyable, and I hope you find the programming at least a little bit challenging to make things a little more interesting. But other than that, that about concludes this tutorial. Thanks for watching. I hope you have a fun time programming and a good rest of the day. Thanks for watching.